Welcome back to another fun and exciting Q&A episode of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
I'm your host for this episode, Heidi Campo, and joining us today is our beloved Professor Fred Watson, astronomer at large. How are you doing today, Fred?
Yeah, very well, thank you, Heidi. And you look as though you're in fit and well compared with the way you've been the last week or two. I hope you're feeling better, but all good here at this end.
Yeah, slowly but surely. I got a little bit of a little upper respiratory, just a cough, a little bit of a fever, but I always just say I know this isn't like a health and fitness podcast, but it's so important to take care of your body. Eat your vitamins. If you're from my generation, you could say eat your Wheaties.
Yeah.
I don't know. They still make those, don't they?
I don't know. I'm not sure what we're talking about. Wheaties?
The Wheaties cereal. It was the breakfast of champions, and they would always put a big sports superstar on the Wheaties cereal box.
Right, okay.
And so in the 90s and the early 2000s, people would always say, eat your Wheaties.
Yeah, of course.
Is the thing of saying, like, that's what you do to be healthier. My house growing up, we'd watch a lot of Popeye, and my grandpa, my grandpa would always read me Popeye. So he would be like, make sure you're eating your spinach.
Yes, of course. That's the certainly the secret that Popeye had.
Yeah, eat your Wheaties, eat your spinach, take your vitamins, whatever you got to do to keep yourself healthy. All right. Well, let's just jump right into our questions from our listeners. So in these Q&A episodes, if you are new here, we do an episode where Fred tells us all about everything exciting happening in space. And then we follow it up with a Q&A episode where you, the listener, ask us your questions and Fred answers them. And sometimes I'll chime in, and when Andrew's back, he'll be chiming in with his wonderful dad jokes. I have not been doing good with the dad jokes. I'm sorry.
It's a relief, actually. It's great not to have the dad jokes.
All right. Well, our first question today is a written question, and it's a bit longer. And this question is from Sam. And Sam says, thank you for your podcasts. Thank you for inviting listener questions and for your helpful answers. It supports making learning a lifelong adventure. There's been a lot of discussion about increasing opportunities to 3D map the universe with our various new telescopes coming online. I am struggling with trying to understand, visualize what is being attempted to be portrayed in the variety of efforts at 3D mapping of the universe, or large subsets thereof. Although the idea of 3D portrayal seems obvious, especially when dealing with something fairly local or close by, it seems to me it would be problematic when we are using the light we receive today, but was emitted millions or billions of years ago. Do the 3D maps show the locations of the galaxies and other structures in the positions they were at when the light we are now using was actually emitted? Or are the galaxy locations manipulated to fast forward them where they would be estimated to be currently? It seems to me that either view would have its problems in portraying a 3D picture, attempting to show relative positions and locations, but relative to what in space and or time? Ooh, this is a really interesting question.
It is. It's a great question, Sam. And the answer is that when particularly when we're looking at great distances, at galaxies that are millions of billions of years ago, light years away, we think in terms of look back times. So we're looking back in time because that's the only thing we can measure. We measure something called the redshift, which is a number that relates to how basically it relates to the size of the universe when the light was emitted. So we measure the redshift, and that tells us how far back in time we're looking for our depictions of these objects. And that's all we have. It's nearly all we have. there is one other thing I'll tell you about in a minute. But the bottom line is that when we build these maps, basically we're putting in look-back times rather than distances. We think of them as distances, but they're look-back times. And so, yes, we are depicting where that galaxy was when the light received, when the light left it, basically. So it's the galaxy positions are not manipulated in any way. It's directly read from the look-back time. The one caveat to that I've mentioned is that galaxies, as well as the flow of what we call the Hubble flow, the fact that the universe is expanding.
I hear a little rooster in the background.
Yeah, he's just seen somebody he knows. That's our dog, believe it or not the rooster. Forgive me if I just go and check that it's what I think it is. Sorry, I'll be back in a second. We can cut this out. Okay, so let me pick up where I was talking about. The caveat, the thing that distinguishes the position of a galaxy from where we think of it in terms of its look-back time, is that we can, for some galaxies, particularly relatively nearby ones, out to perhaps just a billion light years or so, maybe a little bit longer than that, a bit further than that. We can also measure something called the peculiar motion of the galaxies, the peculiar velocity. And what this is the velocity a galaxy has that is a result of local gravitational forces. So if you've got a big cluster of galaxies, they'll be moving around a sort of center of mass. They'll have what we call a peculiar motion, which is distinct from their motion because of the expansion of the universe. I'm not sure whether I'm making this clear. But the way we describe it usually is if you think of a river flowing and you imagine boats on that river, they have their own motion across the water, but they're also being carried along by the motion of the river itself. And that's an analog with what's happening with the galaxies. They've got their own individual motions as well as what we call the Hubble flow, the fact that they're moving because of the expansion of the universe. And you could, in principle, take those peculiar velocities and say, well, if you think about where they are now, those galaxies, their positions will have changed. But in terms of the change compared with the distance that we're looking at, the changes are negligible. That, over the time scales that we are talking about, even though it's billions of years, when you're talking about things billions of light years away, and you're talking about, maybe a few, it's more than millions of kilometers, but it's so small compared with the size of the universe that you would never know the difference. So basically, we just take what we get from our measurement of distance and plot the maps that way. A long answer to a fairly long question, Sam. I hope that explains what's going on there.
Well, that was a really fun question. Thank you for answering it.
Let's take a little break from the show because I want to tell you about our sponsor, Incogni. This is a fabulous tool that you can sign up for and get someone else to clean up all your personal information that's probably been hacked and sold again on the dark web. And now you're getting spam emails, spam calls, robocalls. You're just getting hammered by all these people. Some of them genuine, of course. Some of them are scammers, but you don't know which is which most of the time. So how do you deal with that? Incogni. It's a personal data removal service that helps you gain control of your privacy by automatically requesting data brokers delete your personal information. It handles the legal process for you. If you try to do this by yourself, it could take years. They provide updates on the progress, and it supports global privacy laws. They know what they're doing. It's fast, it's hands-free. It's a very effective way to clean up your act without having to do much at all. And if you'd like to get hold of Incogni to clean up your internet presence and stop getting absolutely spammed to oblivion, use the Space Nuts link to get 60% off your subscription. That's incogni.com/spacenuts. Don't forget to use the code word spacenuts at the checkout. Incogni, Incogni, incogni.com/spacenuts. Now back to the show.
Roger, your last are here also.
Space Nuts.
Our next question is from Mark, and this is going to be a audio question. Mark from Quebec. So we're going to cue that up and play that for you guys right now. So Fred and I are going to get that ready. We'll listen to it and we'll play it for you as well. We're going to play that question for you right now.
Hello, Space Nuts. My name is Mark. I'm recording from Sherbrooke in the beautiful province of Quebec. Now I have a question about the speed of light. So when we talk about the speed of light, we assume it's the speed of light in the vacuum of space, right? I've heard that the speed of light can slow down by something around like 40% when it's traveling through matter like water or diamonds. Now, if an astronaut in space would shine a laser beam through a diamond held at the top of his fingertips, let's say, the light would travel through the diamond at a reduced speed, right? But once the light exits the diamond and is back in the vacuum of space, would it continue traveling at the reduced speed, or would it resume its initial speed? And if it did resume its initial speed, where would it get the energy to accelerate again? Now I know that the light has no mass, but I kind of can't imagine how light could travel at the reduced speed, or how it could automatically return to its original speed after being slowed down. So I would really like if you could help me understand this, how this works. So thank you very much. Great show. Thank you for all your work, guys. Bye-bye.
That's a great question. And it's a little bit like, it's kind of related to a question that we've had some time ago, which is about when photons are emitted, how long does it take them to accelerate to the speed of light? And the answer is they're emitted at the speed of light. And so this question, I think I would tackle it in the same way as I tackled that other question. And that is that light is not just a stream of particles, which, as Mark says, are massless. Effectively, they've got no rest mass. But it's also a wave motion. And that's perhaps the easier way to understand what's going on here. You've got these waves, which encounter a surface, perhaps a diamond or a water surface, and indeed they do slow down. The propagation of the wave slows down. But then when they leave that surface, when they leave that material on the other side, they go back to the same speed. And that's much easier to understand from the point of view of wave motion than it is from the idea of streams of particles. Because the same thing happens in water waves. If you have water waves that are propagating on a surface and they come to a shallow region, their velocity will change. And then if they come to a deeper region, they go back to where they were before. So the speed of light in a vacuum is one of these strange things. It's immutable. It does not change. It's always 300,000 kilometers per second. I think we discussed this in the last Q&A session. We talked at length about it. So quite counterintuitive. And I can understand why your question arises, Mark, but think of it as waves and it's much easier to understand what's going on.
Excellent, Fred. Thank you. Our next question is from Rennie Traub from Sunny Hills, California. And Rennie has a short and sweet question, and it is, how great is the heliosphere around our solar system, and do all or most solar systems have one?
Yeah, great questions, Rennie. One of our regular questioners. They're always good questions from Rennie. This is a good one too. It's only an estimate, although we do have some measurements that lead us to believe this estimate is somewhere near the truth, because we've got 5 spacecraft which are leaving the solar system, and they are, I think, all equipped with magnetometers. The 2 Pioneers, the Voyagers, and New Horizons. I think they've all got magnetometers on board, and it's the heliosphere is the sun's sphere of magnetic influence. And so those magnetometers can basically give you an idea of what the dimensions of the heliosphere are, and it's in the region of it's basically measured in astronomical units. An astronomical unit is the distance between the Earth and the Sun. Something in the region of 100 astronomical units is the radius, and so it's not spherical. It's got a peculiar shape, which is probably because of the sun's motion through the galaxy's magnetic field that distorts the shape of the heliosphere. But it's roughly, as I said, a radius of about 100 astronomical units. So what is that? It's 100 times 150 million kilometers, which is, if my mathematics is right, is about 15 billion. Is that right? Thereabouts, yeah, 15 billion kilometers, something of that size. So it's and the Voyagers are both further than that distance. And so they have sensed the edge of the magnetosphere. We keep seeing headlines, they're leaving the solar system. Well, that's not really quite the case, because the solar system encompasses the Oort cloud, which is a lot further out, but they are probably leaving the heliosphere, the region of the sun's magnetic influence. And to answer your question, Rennie, fully, yes, sun-like stars like ours would have a heliosphere. Some stars are far more magnetic than the sun is, and so they would probably have a bigger heliosphere, depending on the type of star it is. But yet they'll be common to all stars, we think, because magnetism plays such a huge role in the way stars work.
Another good high-impact question from Rennie.
0G, and I feel fine.
Space nuts.
Our very last question today is another audio question, and this one is from Dean in Queensland. And we are going to go ahead and play that audio question for you all now.
Hi, Fred, Heidi, and Andrew. My question is about time dilation, but I've had to break it into 3 parts. I hope that's okay. First part concerns the Kelly twins, whose ages diverge slightly because of time dilation when one of them spent a year on the ISS orbiting the Earth. I've read that a person moving at high speed experiences time slower than a slow-moving person. However, speed is relative. If 2 people in space were moving away from each other at a constant rate, then each one would perceive the other to be the one doing the moving. In that case, what determines which one would have the slower time? This question makes me wonder whether it's acceleration that causes the time dilation rather than just speed. This could explain the Kelly twins' age difference, as the ISS orbital motion is a form of acceleration. Plus, there was also a linear acceleration to get into orbit in the first place. Part 2 is about the idea that an object in a high gravity field experiences time slower than an object in low gravity. If this is correct, is it independent from speed-induced time dilation? And could these 2 effects add together if an object is moving very fast and it's within a high gravity field? Part 3 is about descriptions of time spans in the early universe. Certain events are described as happening within a specific number of years of the Big Bang. However, if time runs slower in a high gravity field, then it must have generally run slower when all the baryonic matter in the early universe was densely packed in a smaller space-time. And if that is true, then the period of 100,000 years from the Big Bang would not be equivalent to a period of 100,000 years here on Earth. Is that correct? I probably have a lot of this wrong. Can you explain it for me? Thanks again for the podcast.
Dean, you don't have a lot of it wrong. I think you've got a lot of it right. The first and second parts of your question, I think, really merge into one, because I think difference in ages with the Kelly twins, I think it was the gravitational time dilation that was being taken into account rather than the velocity time dilation. I'm not sure about that. But both of those effects, you're quite right that accelerations also play a role in this too. Certain for the velocity time dilation, it's what allows the twins paradox to work, because you've got accelerations at the beginning and end of the one twin's voyage to the nearest star and back again. But yes, the gravitational and velocity time dilations, they're both caused by relativity. The two different relativity theories, special relativity in 1905 talked about velocities. And when you get velocities going near the speed of light, all kinds of weird things happen, including the phenomenon of time dilation. A stationary observer will see somebody else's clocks moving slower as they whiz by at nearly the speed of light. And then in 1915, the general theory of relativity, which was about the way gravitation works. And it turns out that gravity does the same thing. Gravitational time dilation. If you're in a gravitational field, your clocks are running slower than if you're outside it. And the closer you are, for example, to the Earth, the slower your clocks will run compared with somebody who is in orbit. I think that was the issue with the Kelly twins. It's microseconds. It's tiny amounts of time when you consider the distance between the Earth's surface and the height of the International Space Station at 400 kilometers. It's a very small difference, but it is measurable. In fact, I think it is even measurable with aircraft. If you fly an atomic clock on board an aircraft, I think from a ground-based observer, it looks as though it's going faster than what we measure time here on Earth. So that's basically sorting out those issues. Your third part of the question, it's certainly true that when we look back at phenomena that are sort of time tagged, if I can put it that way, in the early universe, we do see time dilation. And I'm thinking particularly of supernova explosions, where a star explodes, its brilliance goes up and then decays slowly afterwards. It turns out that you see the decay time changing from our perspective on the gravitational, on 13.8 or however many billion years later when we observe these phenomena. So the same will be true of the early universe, and I think that's taken into account with people's calculations about this. I think time dilation falls directly within the province of cosmologists who understand it obviously a lot better than I do. But yeah, that's the bottom line.
Yeah, and the time dilation is always, it's always so hard to wrap your head around, but you do a great job of explaining it to us.
I just try and put it into terms that I can understand myself, which is not always the cleverest way to do it, but that's all right.
Well, that wraps up all of our questions for today. Fred, thank you so much for always being available to help us out with all of our questions. And to you, the listeners, please keep sending in your awesome, well thought out questions. You guys are really so smart. Every time I read your questions, I'm like, how are you guys even thinking of this stuff? You guys are brilliant. So keep sending in your questions. You only have, like I said, a few more weeks with me before Andrew's back. And so take advantage of that. And I guess without further ado, Fred, do you want to sign us off? Do you have anything else you want to say?
No, just keep the questions coming, exactly as you've said, Heidi. And thanks again to all of our great listeners who sent in questions. Thanks to you, Heidi, for keeping the show going. And we'll see you next time.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.